muted. Okay, you should be able to hear me now. I was on mute. Initially, I was that person. That's awkward. We're going to wait another minute or so for people to join in. And then we're going to go over the 2 question types on the exam. I have one cat next to me on the couch, and my other cat is sleeping in their hammock. So my coworkers are very lively today. Very lively. It's just like having you guys in class. I'm so funny. Except it would be weird if I pet you guys. As a reminder, you can ask questions in the Q&A section, and I'll answer them as I see them pop up. And I'm going to go ahead and get started. So I'm going to kind of walk you guys through the 2 different types of questions, and then I'll walk you through one question type. We'll do an example problem, and the documents that I have up, they're in Canvas on today's date for the live lecture if you want to go look at them. So let's go ahead and get started. So normally every Physics 1 exam is going to have this type of qualitative, quantitative translation. So qualitative means like quality, like you're talking with words and stuff like that. Quantitative is more so numbers, like quantity. So you're having to go between essentially math and words. So this is a fairly high value problem, and on the current AP exam, like meaning before 2020, it is a 12.25-minute question. So on this exam this year, it's still going to be a 25-minute question. I'm just not sure how many points it's going to be. I do know that this problem will account for, I think, 60% of your grade. But you still only have 25 minutes to do it, okay? And then you have the 5 minutes to submit. So qualitative implies using words, quantitative implies using math. So we go from one to the other. So you might be presented with an equation and then asked to, verify that equation or say whether or not it's valid, or a graph or a data set. Sometimes you might be asked to derive equations. I don't think you're going to have to do that on this exam, though, so that's kind of nice. Okay, so things we might be asked to do. We might be asked to work with multiple representations. So you might be given one representation of a phenomena or situation and then asked to create another representation. So what that means is you might be given like a diagram of what's going on, and you might be asked to produce a graph, or in this case, you might be asked to say whether or not a graph is correct, or you might be given an equation and it might ask if the graph presented accurately represents the equation, things like that. So we might have math equations, word descriptions, graphs, diagrams, and data tables. We haven't really done much with data tables, but what you guys are going to want to look for in a set of data tables is kind of those classic, like, if the X column doubles, does the Y column double as well? If so, that's a direct relationship. If X doubles and Y quadruples, then that's a squared relationship. And I did put out a cheat sheet of all those relationships with those corresponding if-then statements, the graphs, and examples from the reference table. Okay. You might be asked to evaluate a student's words. So these are the questions where you're presented with like Abel and Brian and Kane and David, and you're asked to say like which student is correct, or you might be asked to pick out which parts of like student 1 and student 2 are correct versus incorrect. Okay. So you'll be presented with a situation or a question and 1 or 2 students' arguments. You're going to ask to kind of like deconstruct their arguments, identifying correct and incorrect features. Sometimes you'll have to connect the correct or incorrect features to some physics principle or equation. So part A might give you a graph, and you might have to analyze the graph. And then part B might give you something that a student says, and you can kind of verify or discredit what the student is saying by using the graph from above. So you can reference previous parts in later parts of the question. That's what you're really going to see on these qualitative, quantitative questions. Okay. After deconstructing what's right and wrong, you may be asked to reconstruct a completely correct answer. So basically taking all of the right parts, ignoring all of the wrongs, and making it into a statement that makes sense. Okay. You might be asked to evaluate a student's representation. So you might be shown a graph or some equation or maybe even some algebra. And you might be asked to say whether or not it's right or wrong. So these are the questions that you guys don't necessarily like because they're the ones that ask, like, does this graph make physical sense or does this equation make physical sense? And that's where that relationship cheat sheet is going to be really, really helpful. Okay. So as a reminder, things to look at when evaluating a graph. Does it have a slope that makes sense? Okay. So if you were looking at a graph of money you were paid versus hours you'd worked, you would expect that graph to have a nice positive slope because the more hours you work, the more money you're going to make. That's usually how it works. Okay, but if the graph has a negative slope or a zero slope, clearly there's something wrong there. Okay, so that doesn't make sense. So if something doesn't make sense to you, it's probably a good indication that there's something wrong about it. Okay, you might want to think, does it have a y-intercept? That makes sense. Now, we haven't really done a lot with this because we really focus in on slopes and areas. So some graphs should go through the origin, like if you work 0 hours, you should make $0. But other graphs, like height of a person versus age, should not go through the origin because no babies have ever been born at, 0 height. Okay. Should the graph be a line or a curve? Okay, that's one that we've focused in on a lot. So based on the relationship we see in an equation, should this be a line or a curve? Again, where that relationship cheat sheet comes in handy. Okay, so when you're evaluating an equation, you want to think about symbols in the numerator and symbols in the denominator. Okay, so if you have a symbol in the numerator, you want to think, okay, when that symbol increases, say X, does the Y or whatever is on the other side of the equal sign, should that also increase? Okay, so if I increase the speed that something is traveling at, should it also increase in distance? Well, yes, the faster I travel, the farther I should go. Okay, and then if the symbols are in the denominator, remember there's going to be that opposite relationship. So when that symbol in the denominator increases, does the quantity of interest decrease? So that's that inverse relationship. Okay. When you're looking at a student's words, you want to think if the student uses proportional reasoning. So if the spring doubles, then the spring has twice the energy. Those are those if-then statements. Check the equation. So for that, the US, which I've written as PES, is 1/2 kx squared. That shows a relationship that spring potential energy is related not to X, not a direct relationship, but to X squared, which means if X doubles, spring potential energy should quadruple. Okay, so we need to see if there's actually that direct relationship, which in this case there isn't. So that would be a good hint that the student is saying something incorrect. Okay. If the student says that something increases or decreases, like if the ball moves faster, then the time it takes to pass through the photo gate increases. Okay, remember photo gates are like little light sensors that can determine how fast something is moving. The faster it goes through, the less time it should take. Okay, so that doesn't make sense. A faster ball would spend less time traveling through a photo gate. Okay, and then get ready to correct that student's wrong reasoning or explain why it's incorrect. And a lot of the times you can use equations and diagrams and stuff like that in these qualitative translation problems. Okay, so I'm going to check and see if anybody has any questions. Again, if you have questions as we're going through, you can type them into the Q&A feature, or for whatever reason you don't see that, there is still a chat feature that you can use. Okay. But that's basics of the qualitative, quantitative translation. Okay, so let's go through an example problem for this. Nope, wrong window. Okay. So again, this is on the Canvas event for this live. So it says, let me just switch from highlighter to pen. We have a cart of mass M rolling on frictionless bearings and is fitted with a device that launches metal spheres to the left. Okay, so these spheres are going to travel to the left, and my guess is that the device, when those spheres are launched, because these are frictionless, they're not tied down, this is going to move to the right. That's just my guess. Any number of metal spheres can be loaded into the top of the launching device, but the device can only launch one sphere every t seconds. Okay, the device launches all metal spheres with a speed v0 relative to the cart before the speed is launched. So no matter which sphere number we're on, they all get launched with v0. Okay, so suppose that the cart has the same mass as a single sphere. The cart is initially at rest. Okay, that's helpful. And that the cart is loaded with 3 spheres. Spheres are launched at time t equals t. So it's not launched right at 0. We're going to remain at rest from 0 to t. Then 2t and then 3t. And the carts begin to move to the right as a result of the launching of the spheres. Oh, so I was correct in that kind of thought. Okay. On the axis below, sketch a graph of the rightward speed of the cart as a function of time. Use the horizontal grid lines to show appropriate heights and or slopes. Okay. Now, on this AP exam, you're not going to be asked to draw a graph, but I liked this question because I think it has some good thinking of it. And because this is a momentum question, even though there's not a collision. It's kind of a reverse collision. But I like this question a lot. Okay, so the initial momentum of the cart sphere system is 0. Okay, so again, we're cart and sphere system. Okay, so we're initially at rest. Everything's at rest. From 0 to t, I have no velocity. Okay, when one sphere is launched, okay, if this mass and this mass are the same, and this is launched at v0, then the cart also has to move at v0. Nope, just kidding. v0 over 3, because we have. Okay, so I did this out beforehand and forgot to look. Let me show you what I'm doing. So we have initial momentum has to equal final momentum because momentum is conserved. Initially, we are moving with a momentum of 0. Afterwards, okay, we have one ball moving to the left at v0. So that has a negative mv0. Okay. Then we have 1, 2, 3 mass. So 3m moving at some unknown speed to the right. Okay, so m v0 is 3mv. So v is the same thing as v0 over 3. Okay, so whatever this first time interval is, the velocity is at v0 over 3. Okay, and that velocity is going to be constant because we are on frictionless bearings, okay, which means there's no external force to speed up or slow down that cart, okay, with the exception of that change in momentum. Okay, so then we can kind of analyze another system, okay, to make our life a little bit easier. So now I'm going to think of the cart sphere system with just the 2 spheres. Okay, so I'm ignoring the fact that the 1 has already left. So initially that system is moving with a mass of 3m, the cart plus 2 spheres, at a speed of v0 over 3. One of the spheres is launched, and I'm left with a mass of 2 afterwards. So this simplifies to mv0 plus 2mv. So I add this mv0 to both sides. So this is 2mv0 equals 2mv. So during this time, we are at a speed of v0. Okay. Now for the last section. For the last section, I'm just going to do the CART single sphere system. And you can change your system to make your life easier as you go through a problem. So this CART sphere system has a mass of 2m at a speed of v0 initially. The last cart is launched, and we're left with a speed, or the cart just moves forward with a speed mv. So this gets added. No, stop. Oh, that's annoying. Hold on. Let me undo that. There we go. Go away. Stop. Stop. I don't know why it's doing that. There we go. Okay. So we're going to add this mv0 to both sides. And then we have 3mv0 is mv. So the cart moves afterward with a speed of 3v0. Okay. Now, the reason why I wasn't graphing as I went with each one is because I didn't know how I was going to be able to set up these intervals. So it looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, what am I trying to say? Bars, graph lines. Okay, so I need to end at 3v0. So let's say 3v0 is up here, which was 9 bars. Okay, so that means v0 occurs at 3 bars, and v0 over 3 occurs at 1 bar. So I did choose a scale that was easy for me to divide by 3 twice. So essentially it was like, what's 3 squared? Sorry, my writing's so terrible. Okay. So on the AP exam, you're not going to be asked to graph like this. This is actually a really long problem to do, and there's definitely a shortcut way to do it. I prefer this way. This also isn't officially an AP exam problem, but I just really like this problem. So what you might be asked to do on this year's exam is you might be presented with this graph, and you might be asked to verify whether it's correct or not. So things we might want to look out for on a graph like this is there being slopes when there shouldn't be, either positive or negative, or the step increases not being proper. Okay. So then in question A2, we have a student attempting to predict the speed of the cart after all 3 spheres are launched, reasons this way. So they say that all 3 spheres were launched to the left with an initial speed of v0. Conservation of momentum applies here. So far, this is correct. I'm doing a terrible job at underlining. This is correct. Okay. So I'm just underlining the things that are correct, because anytime you're presented with a student's reasoning, you'll probably have to say whether or not it's correct. So they are launched to the left with a speed v0. Conservation of momentum does apply here because there's no external forces, okay, because there's no friction. The system begins with 0 momentum. That is also true because we start at rest. Okay, so this means that the leftward momentum of the 3 spheres, okay, equals the rightward momentum of the cart. Okay, so the cart's speed is 3v0. So let's just do a mathematical equation real quick to see if that is correct. So after all the spheres have been launched, I realize I'm kind of off screen right now, they each have a momentum of minus mv0 because they both all have a mass m and they're all launched at v0. So the student's saying, well, if momentum is to be conserved, then the cart of mass m should be moving at 3v0. Okay, and in order to conserve momentum, that whole equation must equal 0. So let's see. Negative mv0, this equals negative 3 mv0 plus 3 mv0. Oh, well, that does in fact equal 0. Okay, so actually everything about the student's explanation is correct. Okay, so what we would write is we would say student is completely correct. Okay. The system of 3 spheres and carts starts at rest. So P total momentum is 0. There are no external forces. So momentum is conserved. Since the total leftward, that's not how you spell left, momentum after all spheres are launched, I'm having trouble spelling, is negative 3 mv0. The cart must have a rightward momentum equal to 3 mv0, so P total equals 0. So velocity of the cart is 3v0. So you're just explaining why what the student said is correct. Okay. So I'm just going to check in and see if there are questions real quick once my keyboard reconnects. Okay. That is something squared in it like kinetic energy. Will the formatting be messed up if we copy and paste it to submit? So it's my understanding. So somebody had just asked if you're typing in your equation and you are doing like 1/2 mv squared, which you can do subscripts and superscripts in Word very easily. If you copy and paste, will the formatting get messed up? I honestly have no idea. I haven't tried. That's a great thing to try in the AP exam demo. So type in like the kinetic energy equation, then copy and paste it. But it's also my understanding that there shouldn't be any, what am I trying to say? Any algebraic manipulation on the AP exam. That being said, you could type out the kinetic energy equation as KE equals 1/2 M times V, and then do the up caret squared like I just showed in the chat. And that should have no problem copying over, and you would get full credits to that. Or you can type it out. Like you could say kinetic energy, or write it out. Kinetic energy is 1/2 times the mass times the velocity squared. I'll try that square thing today and let you guys know. That is a very good question. Let's see. Where is the AP demo? I sent out a link to it earlier today. If you go on Canvas, you can also find it on today's date, because I want you guys as an assignment to go through and do it and just show me a screenshot of you completing one of the questions, so I know that you know how to kind of go through and do everything. Okay, so I'm going to go back and we're going to go over everybody's favorite, or actually no, I need to finish this question. Okay, so this question. So we have 2 other students attempting to create an equation that gives a final rightward speed VF of the cart in terms of the relative leftward launch velocity of the spheres. The carts of mass M, the mass of a single sphere M, and the number of spheres loaded into the launcher N. So they're giving us all of the variables that could be in this equation, explaining what they are. After several experiments, the student's analysis of the data yields two equations. So student A says V final is the square root of V0 mass of the car over N mass of the spheres. Student B is V final equals V0 square root M over N mass of the sphere. So it looks like the only difference is where this V0 is between the two equations. So one has it inside the square root, which means V final and V0 have a square root relationship. Student B has it outside the square root, which means that V final and V0 have a direct relationship. So part of the student's experiment involved changing the relative launch speed of the spheres. The student plotted a graph of a function of V final versus V0. So the final velocity of the cart versus the launch velocity of the sphere. For which student's equation does the graph give the best support? So I'm looking at this graph, and this graph looks very linear, okay? So linear graphs correspond to direct relationships, okay? Direct relationship should look like V final relative to V0, or in an equation, V final is A V0 over B, or C, or square root of D, whatever, as long as V0 is in the numerator. So the only equation between student A and student B that matches with this linear graph is student B. Okay, so how do we explain our reasoning? We could say the graph is a line which represents, sorry for writing sideways, a direct relationship. Only student B's equation has a direct relationship between V final and V0. Okay, so we've talked about how we know from the graph it's a line, and that means direct. And then we've talked about which student's answer choice represents direct. Okay. So then B2, a third student inspects the two equations written by the two students and declares that both equations exhibit the same fundamental flaw, making them both incorrect. What could be incorrect about both equations that would make them invalid? So if you were thinking while looking at these, like, we've never done a problem dealing with momentum where there are square roots. It's very strange that student A and student B have square roots in their relationship or in their equations. That's the part that's wrong. Okay, so both students have square roots in their equations, which is definitely not correct with momentum, because momentum is only based on P equals mv. Okay, there's no square roots, no nothing. The only time we would see a square root with mass and velocity is if we were doing kinetic energy. But we didn't really look at kinetic energy in this problem. Okay, so we would say something like both students are incorrect because the equations have square roots. The equations come from the conservation of momentum equation. Okay, and we could say something like P final is P initial or whatever, but you can just say the conservation of momentum equation and people will know what you're saying. And this equation only involves inverse and direct relationships. No square roots. My writing got really bad there for a minute. Okay, so we talk about why it's wrong, where they go wrong, and essentially kind of how to fix it. We say only direct and indirect relationships. Okay, checking again for any questions. It does not look like there are, so let's go on to paragraph responses. Okay, now paragraph response questions are notoriously difficult because the AP exam asks for a lot of really random stuff to get full points in a paragraph response question. And to be honest, I don't think any of the AP physics teachers, if we were to take a paragraph response question, I don't think we would get full credit. We'd probably get 6 out of the 7 points, but we'd probably miss something. So you shouldn't be striving for perfect credit on a paragraph response question because it's hard to do. Okay. So paragraph response questions. These are usually 7 points and 12 minutes. Okay. On this exam for this year, it's going to be about 40%. Okay. And instead of 12 minutes, you guys will have 15 minutes with 5 minutes to upload. Okay. Usually these questions have a part A where you are ranking or something like that. And then in the paragraph, you are explaining something about the ranking or something like that. Okay. So when you're composing a paragraph, try to follow ABCs. We want to actually answer the question, step 1. We want to talk about basic physics principles. We want to cite information, and then we want to make a conclusion paragraph. Okay. So when you're approaching a paragraph response question, you'll see me when I do these out in practice. I usually make a bunch of bullet points, and then I take those bullet points and translate them into a paragraph because that's just how it makes sense to me. Okay. So step 1, answer the question. First thing we have to do is clearly and directly answer the question asked. So on some problems, you're given predetermined answers. You have to put a check mark. If you're not given these, then make sure you're answer the question in a way that isn't ambiguous. So if you're asked to say whether something increases or decreases or stays the same, the first sentence in your paragraph should be XYZ increases or XYZ stays the same. If you're given 2 or more cases to choose from, state which case answers the question or clearly state that both cases are the same. Okay. Or you say, like, trial 1 differs from trial 2 in such and such a way. You should not say that something just changes. I need to know how it changes. And I think that I've nitpicked this on your test enough that you guys kind of understand this by now. You want to talk about how that thing could change in either cases or both cases, but you have to commit to an answer. You can't just like ramble on. Okay. So in some cases, the answer is given to you already. So for example, you might be asked to say, explain why the sun is brighter than the moon. So instead of saying which is brighter, the sun or the moon, explain your reasoning. Okay. So you might be already given the answer and asked to explain why, or you might be asked to choose an answer. Okay. In these cases where the answer is already given to you, you only really have to do the basic physics, the citing information, the drawing together. Okay. So basic physics. Your explanation has to include at least one statement of basic physics. Conservation of momentum, conservation of energy, Newton's second law, meaning the idea that force is equal to mass times acceleration. Newton's third law, the idea that forces in any interaction are equal and opposite. You can talk about impulse being a change in momentum, meaning force times time is change in momentum. You can talk about energy and momentum and Newton's second laws. They relate to rotation, things like that. Okay, so you'll know it's a statement of basic physics because it's true all the time, every day, forever. So basic physics can be the names of laws like Newton's third law, like I said, or a statement of the law itself. So when a horse pulls the cart pulls back with the same force. Here's the fun part. Basic physics can also be equations. So it could be a relationship. So you might say kinetic energy is 1/2 mv squared. You can talk about equations in your paragraph. You just can't only use equations. So you could say kinetic energy is related to velocity squared, not directly related, or something like that. Or you might say if the net force is the same either way, then mass and acceleration are inversely proportional. So that's the idea that F equals ma. So if F is constant, as you increase m, a has to decrease. That's what that second sentence says. Okay? So you need to talk about some type of basic physics. You're either stating a law, an equation, something like that. You gotta include physics in a physics answer. Please don't step on my papers. And then you're gonna cite important information. So this is when you point out important aspects of this particular situation, not some random situation we did in class, this one, okay? So it should say in this situation, or in case one, or for the small cart. Be particular, be exacting. Pretend that the person reading has no idea what's going on. You have to be explicit and, yeah, explicitly say what you're going to say. Okay. If you're presented with 2 or more cases or 2 or more objects, you should consider doing a compare and contrast. So compare what's the same. They have the same mass. They start at the same height. Acceleration due to gravity is the same. And then contrast. Well, they have different slopes. So I'm thinking of like a mass going down a hill. They have different slopes, so the acceleration is going to be different, which means the time is going to be different. But conservation of energy says that the velocity is going to be the same, so they reach the same speed, but at different times. Something like that, okay? So specifically, in which case is some quantity more or less? So what's the same, what's different if you have 2 different cases, okay? Then you're going to draw it all together. Woo! Make a nice little conclusion sentence. So this is when you take your statement of basic physics and the important information you cited and draw it all together, okay? So depending upon how well you do your B's and C's, your draw it together might only be a single sentence. So it might be something like, because of what was stated above, this is why case 2 ends quicker than case 1, right? Kind of thinking back to the 2 blocks going down a hill. Right? Because of energy conservation, because of everything that's the same, and so on and so forth. But you should have some sort of like drawing together concluding statement. Okay. We don't use claim evidence reasoning, so ignore that. Right. So we're going to talk about building nice physics sentences, because you should not be using the word it at all. You shouldn't say it increases, it decreases, it stays the same. You should be very specific, and you should say cart A increases in velocity, cart B blah 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 blah. Okay, so sentences have to exist with a subject and some sort of action. Increase, decrease remains the same. Okay, you don't have to be like writing these gorgeous, beautiful, eloquent sentences. They can be short. You don't have to have crazy punctuation or colons or semicolons, because who knows how to use those anyways. I don't. Okay. They just need to be short and to the point. You're not trying to write a 500-word essay. You're just writing a paragraph. So some good nouns. Good nouns are either objects in the situation you're presented with, pieces of lab equipment, or look, our quantities on our reference table. Okay. So those are your nouns: length, mass, speed, velocity, area, height, whatever. Okay, those are good nouns. It is not a good noun. Them, not a good noun. Okay? Be specific. Okay, so your nouns are going to do things. Your nouns are going to speed up. You're going to slow down. You're going to change direction, gain, transfer, lose energy, gain, lose, transfer momentum, exert or experience forces, blah, 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 blah. Lab equipment makes measurements. I don't think you'll have to do anything with lab equipment this year, but as a reminder, spring scales and force sensors measure force. Photo gates measure velocity. Motion detectors measure velocity and acceleration. Meter sticks measure distances. Stopwatches measure time. Slow motion cameras can measure velocity and stuff like that as well. Quantities like the one in the AP physics tables will increase, decrease, go up, go down, remain constant, be the same, be greater, be directly proportional, be inversely proportional. Those are all good nouns to use as well. Don't do these things. Okay? Don't write it, they, them. It's a sign that you don't know what's going on. If you're saying it, they, them. If you can't specifically say what's increasing or decreasing, that kind of lets the reader know that you maybe don't know what's happening, okay? And could result in you not getting points for that statement. Even though your statement might be correct, if you're not using the specific noun, then the AP reader can't be sure that you know what you're talking about. I don't grade your tests. Somebody else out in the continental US grades your tests, not me, okay? Don't restate the question. Again, it's not English. You're not going for maximum words. It's not a DBQ. Okay. And don't just repeat it back to the greater information that you were given. You have to kind of talk about what information you can infer from the problem. You can say things like the cards have the same mass, the cards start at the same height, but don't just like list them. Talk about why that's important. So if they start at the same height and they have the same mass, then they have the same potential energy in the beginning, okay? So it's kind of like list the things and then say why it matters, okay? Don't write more than you need to. More words don't mean more points, and more often than not, the more you write, the more likely you are to contradict yourself, which is bad. Okay? If the grader has trouble finding the correct parts of your response, you may not get points at all. If you include extra information, you're not going to get full points. If you include incorrect information, you're not going to get full points. Okay? So if the question really only deals with momentum and forces in a collision, don't start talking about energy. If you don't need to talk about energy, then don't talk about energy. Okay? Never just say force. Say which force you're talking about. The force of friction, the force from the collision, the tension force, the force of gravity, the centripetal force, which is just another net force, things like that. Normal force. Okay? So talk about which force you're talking about, or the net force. Never just say energy. Say which type of energy. Never just say field. Fields probably won't be so much on this exam. Never just say rate. Okay, say what information is changing with time. So the rate of distance, the rate of velocity, the rate of acceleration, the rate of momentum, right? Okay. Never just say components. Say which vector components you're referring to. So you might want to say the components increase. And the components of what? My fingers are components. Are my fingers increasing? Right? No. You might want to say the components of the force of gravity are increasing, or the components of the momentum are increasing. Okay? It's very similar to how I harp on you guys with units after all of your numbers, because without units, your numbers are meaningless. It's the same sort of thing. These words like force, energy, components, they're meaningless without that quantifying word, like component of force or kinetic energy. Okay? And the last thing, never, ever, ever, ever say that something moves. That doesn't tell us a lot. Okay? It's a terrible thing to say. Okay? And I know that I say that sometimes in class. What you should say is that something moves with a constant speed, or a constant velocity, or a constant acceleration, or it moves with increasing acceleration, decreasing acceleration. It moves with uniform circular motion or non-uniform circular motion, which just means that the speed changes as it goes around, or it moves in simple harmonic motion, or it oscillates back and forth, or it speeds up and it slows down, or it, things like that. You want to be as specific as humanly possible. Okay. And this example is silly. We're not going to do that example, but I'm going to check and see if you guys have any questions on that real quick. And it looks like not. Okay. So we're just going to run through an example problem for this paragraph, and then we will be done. Okay. So I have two identical cars approaching an intersection at the same time as shown in the diagram. So they're approaching the intersection here. Car A takes a left turn. Okay, so car A follows that path, and car B takes a right turn like that. neither car changes speed. So we're moving with constant speed. Remember, if we're moving in a circle, we can't say constant velocity because our direction is changing. During its entire turn. Which car is most likely to lose control? Okay. Well, just thinking out loud, if I'm losing control, it's going to be because my tires start like slipping against the surface. And slipping against the surface makes me think of friction. Okay, so I'm probably going to have to talk about friction. Okay. Now, I'm also, when I look at these problems, I notice that these cars are making semicircular paths when they turn. Okay, so that also means I'm probably going to need to talk about centripetal force. Okay, so they're two identical cars. So A and B have the same mass. Okay, that's good, awesome. And they're the same speed, so they're moving at the same speed. Okay, cool. So I'm noticing the thing that's different is the radius, right? A has a much larger radius. Okay. Oh, and they're on the same surface, which means this force of friction, they have the same mass and the same surface. This force of friction is also going to be the same. Okay. So I've thought about, I haven't done it in a paragraph yet, but I've thought about what's the same. I've thought about what's different. So now I need to actually answer the question. Okay. So let's see. This centripetal force, well, we're going to be moving in this circle. The force causing us to move in this circle is the force of friction. Okay, so force of friction is mv squared over r. Okay, so if m and v are the same, and this force of friction is the same, okay, the larger this radius, the less the force of friction actually needs to act. You might be thinking, Narc, how can friction change? I thought it was the same. Well, remember that when we're going in a circle, we're dealing with the static force of friction, which is variable up until some maximum amount. Okay, so the larger the radius, the less the static force of friction has to act. So what that means is if we decrease the radius, this force of friction is going to have to increase, which might mean that we reach our maximum value, which might mean that we exceed the static force of friction, which might mean we start slipping, aka losing control. So car B is going to lose control first. Now I have to explain why. Okay. So I'm just going to rotate this so I can actually write better. All right. So car B will lose control first. Okay, so there's my answer. Okay. Now, instead of talking about physics principles first, I'm going to start listing or citing my evidence. Okay, so both cars travel in semicircular paths at a constant speed v and have a mass m. Okay, so that's a little bit of citing. Okay, so then I'm going to say the force causing these cars to move in a circle is the force of static friction. Okay, so this is a mixture of basic physics and citing some evidence. Okay, all right. So we can say something like the centripetal force needed will depend on the radius of the path, since mass and velocity are the same. Okay, so again, a little bit of B and a little bit of C. Okay. So this means that as the radius of the path decreases, because I want to talk about why B is going to lose control, so I'm going to talk about B having the lower path. So this means that as the radius of the path decreases, the centripetal force and therefore the static friction force will need to increase. However, static friction force has a max value. So a small enough radius could cause a car to slide, losing control. This is what could occur for car B. Okay, so again, this sentence here is citing evidence. The radius of the path decreases, so centripetal force and therefore static friction force will increase. Again, more citing evidence. However, friction force has a maximum value, so a small enough radius could cause the car to slide, losing control. Okay. This is what could occur for car B. That's me drawing everything together because I forgot this last part. Car B has the smaller turn radius. There, now I've officially put everything together. So I've referenced that's why, you know, the difference between car A and car B. And then if we work backwards, we can see why car B has the better chance of losing control. Now, in this, they gave me some words that I might need or could use. So I talked about static. I did say the same. I talked about speed. I talked about friction. I talked about forces. I didn't really talk about coefficients. I talked about centripetal. I talked about constant velocity. I talked about radius. And things like that. I talked about inversely proportional. I essentially did. It said, you know, as the radius decreases, the centripetal force will increase. Okay. So having this sort of list over here helped me figure out the answer. Now, what you could also do is you could start writing out your answer with all of that citing evidence, talking about what's the same and what's different. And that might help lead you to an answer as far as what's going to be the better option in a case like this. It's whatever's going to work best for you. Okay. So now, any last minute questions on how we do these? As a reminder, you guys over the next 2 weeks have to do a total of 6 practice problems, 3 QQTs as they're called, and 3 paragraph. You have 4 of each to choose from. So you have to do 3 of the 4. And then you have to do 2 of the 3 multiple choice that are up in AP Classroom. Okay. It doesn't look like anybody has any questions, so I'm just going to go ahead and say so long. I see you guys soon. Bye.